You've now seen how we generate models, verify that the models and schematics are functionally equivalent, and verify the functionality of the schematics. We now want to show you how straightforward it is to verify all of the block level models, make sure that they are all in the cadence hierarchy, and make sure that they are always up to date. This is also a necessary step for chip level verification. To demonstrate how we do this, we're going to use a buck converter as an example. Our starting point is that there is a snapshot of the block level schematics, and that the MiM specifications have been entered for all of the blocks. We could go top down where only the MiM specifications are available, in which case this step of block level verification would be skipped and you would move on to system and chip level verification, which we'll show you in the next video, and return to block level verification when the schematics have been completed. Here on the specifications list page, we're going to select manage and enter information for all of the blocks that we want to verify. What we now see is a list of the specifications and operations that we can do on them. And now we can perform the operations that we were able to do with AV, as shown in some of the previous videos. We can download the specification from the generator into your local directory. We can publish all of the files that are generated into the Cadence library. We can do a pin list comparison between the model and any number of views. This indicates the configurations we want to simulate, including model versus model or model versus implementation. This allows us to create a symbol from the MiM specification in case we're going, for example, top down and the symbol doesn't exist yet in the Cadence library. The reference specification is also set up for system Verilog, so I'm going to do a model versus model for the system Verilog, which is SVS, and a model versus implementation for the system Verilog, which is SVI. The tool we're going to be using for manage is called AutoMIM, and just like with AV, there's an initiate command. We're going to copy the initiate command. Now if I go back to the Unix window, here in my working directory I only have cdslib, the log file for Cadence, and a lock file. I'm going to put up a clock on the screen just so you have an idea of how much time will have elapsed as I run the command. Now I'm going to paste the AutoMIM initiate command. And now I'm going to launch the command and speed up the video. In this case, approximately 21 minutes will have elapsed. Let's go ahead and take a look at what this result means. First, there are 14 repositories or blocks where operations were performed on those blocks. The first operation was downloading from the MiM server into the local directory. The next operation was publishing from your local directory into the Cadence library. Then the simulations were run. And here's the simulation summary. There were 14 model versus model or Verilog AMS versus the same Verilog AMS. There are 14 model versus implementation or model versus schematic. So the Verilog AMS versus the schematics. There was one system Verilog to system Verilog model, and there was one system Verilog versus schematics. Recall that that was for the reference, where there is system Verilog available. Out of all of the simulations run, 30 in total, there were no failures. In total, there were 5,850 tests, and there were no failures. We also provide the capability to waive failures, and this is just saying that no waivers were found. Now, if we go back to the library manager, and we refresh, we'll see that the MiM views are now present, including the Verilog AMS model, the specification, and a PDF for the specifications. For the reference where system Verilog was available, we also see the system Verilog model. In addition, the test bench views are now available. We see the test bench, and we see the model versus implementation and the model versus model config views. For the reference, where system Verilog was available, we can see the system Verilog view for the model. In the reference test bench, we also see the system Verilog versus implementation and system Verilog versus system Verilog config views. There is only one test bench because we want the test bench to be consistent regardless of what language is used for the model. So now if I go through all of the blocks, you can see the various views present. Now back in our terminal window, where we had seen only a few files, we can now see that there's a directory for each of the blocks. These are the working directories. The simulation log files are here, the simulation text summary is here, the waveforms are here, And these are for all of the configurations, meaning if model versus model and model versus schematics were run, then both of the results are here. The netlist's schematic is here, and data from the simulations are stored in a machine-readable way, so that scripts can be written to analyze the simulation results. Our general philosophy is to make it easy for the user to add automation. In this directory, you can run AV as before, either just to view the simulation summary and waveforms, or continue to work on the block, such as re-downloading the model, publishing it, netlisting, and resimulating. Let's now go ahead and break something on purpose and see if AutoMIM Manage detects the change. I'm going to go ahead and make a change to the reference block. I'm going to change the MiM specification so that the trim works slightly differently. Instead of 5 millivolts for each trim setting, I'm going to change it to 6. I'll go ahead and update the model and close the page. We can see now in the revision column that the reference specification has been changed. Now let's go back and run AutoMIM Manage. As before, I'm going to bring up an X clock. And now I'll run AutoMIM Manage. As expected, we see that the reference failed in the model versus implementation or model versus schematic comparison. We changed the MIM specification, which changed the model, and of course we didn't change the schematic, and so now there was an inconsistency. Out of the total 195 tests that were run, there were 45 failures. In the simulation summary, we see the one failure, we see that it was the reference that failed, and it was in the model versus implementation or model versus schematic configuration. And we see the 45 unexpected failures. We see the one failure out of all the suites, and we see the 45 failures out of all of the tests. If we didn't know why, the next natural course of action would be to debug the simulation. I'd go into the reference directory, and I'd first look at the simulation summary. I'd see all the different failures, and here I would notice that as the codes approach 0, that I don't see any failures. And then as the code increases and get further away from 0, I see failures again. And this would make sense based on my multiplying by 6 instead of 5. For the codes that are closer to 0, the error won't be as great, but for the codes further away, I would accumulate error and I'd see a bigger absolute error. I could also bring up the waveform viewer. Here I'll go ahead and plot adjust, the enable, and then the two outputs, one for the schematic and one for the model. It's hard to see what's going on from this view, but if I plot test and failures, then I can see exactly where the failures are. The failures are here, but they're not here. If I zoom in, I can see in the waveform view what I saw in the simulation text summary, that there's failures around code -9, -10, -11, -12, but that -8, -7, -6 are okay. And I would debug from here to see exactly what the differences are between the schematic and the MIM specification. Let's go back and fix the reference by using the revision control system to revert the change back to revision 4. I'm going to select create and restore here. I can see the various revisions here, and I'm going to go back to revision 4. I'll run it again to show that the results are clean. As expected, there are no failures. In conclusion, we're now ready for chip and system level simulation. All of the models are in the Cadence library. We have verified that the models are functionally equivalent to the schematics, and at any time before tapeout, all we have to do is to rerun AutoMIM Manage for block level verification and to push model changes into the Cadence library. Thank you for watching. Please click in the upper left for our next video. Please click in the lower left for the playlist of all of our videos in this series. Please click on the right to subscribe to our channel.